Okay, welcome to this evening's presentation of James Webb Space Telescope. This is something that's been long in planning, and we've been waiting patiently. We were expecting the launch to take place this coming Saturday, but it's actually been moved out a few days to the middle of the week, waiting with bated breath. So next week, the following week, we'll have a status update. James Webb was a NASA administrator from February of '61 to October of '68. He believed that NASA had to strike a balance between human spaceflight and science. So that's how he was essentially awarded the reference to James Webb Space Telescope, because of the fact that he understood that you can send people to the moon, but you also need to do the scientific instruments. And the JWST was originally named the Next Generation Space Telescope, but then they gave it the commemorative name. Some of you have might heard that there's some rethinking of the name of the telescope, but it will be the JWST or the Webb until after it gets deployed, and then they're going to give a final verdict on what they want to call it. But at the moment, and as far as I know, it's JWST. So you're used to hearing me blather on about subject matter, but tonight we actually have a subject matter expert. He's from the Space Telescope Science Institute. He's Dr. William Fischer. His focus right now is on the Hubble Space Telescope, the Cosmic Origins Spectrograph. He's a support scientist for that instrument. And before the session started, he and I were discussing being thankful that the HST is back online doing science again. So the first folks I have to thank for this are the NASA Goddard Space Flight Center, who were the folks that approved us for doing this event. So that's the picture of their campus in Greenbelt, Maryland. The second thanks I have to give is the Space Telescope Science Institute in Baltimore. They coordinated sessions and provided us with the subject matter experts, and coordinated dissemination of physical content for those presenters that are actually doing live face-to-face sessions. There were handouts, but I can't hand things out over Zoom. So I'll just point to them or reference them on the web, and people can go look them up. So a telescope in space. The Earth's atmosphere gets in the way of observing all that moisture, the sort of ripples that you see down a heated highway. That makes it difficult to see through our atmosphere out to things in space. We might be able to see them, but to get a lot of magnification and to get still images, we've had to resort to things like putting telescopes at very high altitudes in dry desert plateaus, using lasers as artificial stars to deform or adjust the image in real time to get rid of the disturbances in the image, or observing in radio, which passes through the Earth's atmosphere. But the Earth itself can actually get in the way. So even if you have a telescope that is at a very high altitude and has clear skies, the thing that you want to look at, maybe on this side of the Earth, and your observatory is at that time of day on the other side of the Earth. And then when the Earth rotates around, the target may have done whatever it's going to do, or it may be in a different part of the sky, and you can't see it. So there are limitations to observing from on the Earth, even at a high, dry spot. There are also issues with putting the telescope in orbit about the Earth, because the Earth still gets in the way. If the telescope happens to be orbiting the Earth and the target you want is on the other side of the Earth, you have to wait until it orbits around to see it. Also, there are magnetic field distortions in the Earth's magnetic field. One of them is the South Atlantic Anomaly, or the SAA, and the Hubble Space Telescope, as it orbits at an inclined orbit, and so it will periodically pass through the SAA. When it does that, it might have to turn off instruments or stop observing because of the radiation that comes in and might distort the images. So you can put a telescope in solar orbit. That's better, but it has its own issues, like the sun. You need to put it someplace where it's going to not have these problems. Also, if you remember from the Hubble Space Telescope, Hubble was put into orbit by the space shuttle, but it had to do a couple of servicing missions afterwards. And you're not likely to do that if your space telescope is at Lagrange Point 2 or in a halo orbit about it. So Lagrange Point, L2, the Earth orbits the sun. And the Lagrange points are gravitational stability points in the orbit. Anytime you have an object orbiting another object, you can have these 5 points where if you put a spacecraft there, it's not on a perfectly free ride because solar radiation will push on it, but it doesn't take a whole lot for it to stay relatively in the same spot. And there's a nice spot called L2 that is, if you see, you can have the sun, and then the Earth, and then the moon, and here's L2. And you also see that this elliptical orbit is called a halo orbit because L2 is here and it orbits about in kind of an ellipse, which is kind of like a halo. So the L2 point is already being used by other instruments. The European Space Agency's Gaia or the Russian Spectroscope, they've also been at L2. And when your spacecraft can no longer do its scientific observing, the goal is to move it out of wherever it is in L2 so as to not crowd up the parking lot. So if you think about the Earth, and the Hubble Space Telescope is orbiting the Earth at 570 kilometers. The moon is 384,400 kilometers. The Webb will be out at L2, which is 1.5 million kilometers. Not a place that we have a spacecraft to go service it should something go wrong. This is an all-encompassing diagram of once the Webb is launched from Earth, it needs to go on about a 30-day mission to get out to the L2 and to put itself into its halo orbit. It'll take about 60 days, 30 days of which is to get there, and then another 30 days of which is for calibrating and prepping the instruments for observing from the L2 point. But we won't actually start getting observational data for about 115 days because they need to take test images, they need to check the stability of things, and they need to take some, let's say, nice pictures courtesy of the Webb to be put on the Webb. There is a video that I've got a link down to here that will be in the link at the end that is actually about 10 minutes long, and it shows all the opening stages of the JWST. And it stages sort of, you see it do something, and then it says what it did, and then it opens up this, or it'll open up that. All of those things have to work 100% in order for the Webb to be usable once it gets to the L2 halo point. The thing to note here is it's going to take a while to get there. It's going to take a while to get everything ready. And then it's not going to be precisely at L2. It's going to be at an elliptical orbit about L2. You'll also often see people saying, well, why don't you put it in orbit around the moon? Or why don't you put it on the far side of the moon? Confused with the dark side of the moon, which there isn't. And the reason for that is you still have other things that will bother the instrument if you're trying to do infrared, like the sun. So if you think of it as, if we have the Earth, and we have the deep space network, which is used for radio communication. If we put the telescope on the far side of the moon or in orbit so that it's in a synchronous orbit where it always points away from the moon and away from the Earth, how would you do radio communication with it? You'd have to actually put additional satellites in orbit about the moon as relays to get the data out to it. So if you move it out even further, and then you put it in a halo orbit, it solves those problems. And then there's pointing. So in its halo orbit, the bottom side of the telescope faces downward towards the moon and the Earth and the sun, so as to block out that sort of interference light from the telescope. So you'll never see the Webb taking a picture of the moon or the sun because that would expose the instrument to the sun's heat and light. Not good. So now I'll bring out my prop model. Some of you may have seen this before, but in addition to having a picture, I've got 1,000 words. I've got actually an object here that you can. So this is the model of the James Webb Space Telescope, and it matches the picture. So as you can see, it will sit like this, and the bottom side will face towards the Earth and the sun and the moon. And so you have 2 radio antennas here for different bands. One is for lower speed data, one's for higher speed data. You have the solar panel, which powers the instrument, and it faces like that. You also have the rocket thrusters for maintaining the orbit. They're on the bottom side, so as to not get debris into the telescope. And then the telescope can rotate around to look at different targets. And it can tilt a little bit this way and a little bit this way, about 5 degrees each direction. But if it goes too far, obviously it'll be pointing towards the sun, and that's not good. To keep it cool, there's a couple of things. You can see the multiple layers of reflective foil. That will keep it cool, and there's actually gaps between the layers to let the heat exhaust itself. And on the back side, right there, there is also a radiative cooling set of fins for the instruments. So when the instruments in their operation produce heat, this will draw the heat off the instruments to keep the instruments cooler. So people will often try and compare the Webb to the Hubble Space Telescope. So I've got some comparisons here. Here's the Hubble Space Telescope and the James Webb Space Telescope. If you're familiar with how astronomers name instruments, they're pretty simple names. The Very Large Telescope, the Extremely Large Telescope. There's the Hubble Space Telescope and the James Webb Space Telescope. Well, it's a telescope in space, so what else would you call it? So here's the locations. Hubble is in low Earth orbit. He was put into orbit aboard the Space Shuttle Mission 31 back in 1990. It's been up there a while. The Webb will be in a halo orbit at L2, about 1.5 million kilometers or 932,000 miles from Earth. They'll observe in different wavelengths, different bands. The Hubble will observe near infrared through visible to far UV. The Webb is more focused towards the infrared region. So it'll go from middle infrared to near infrared. It'll actually get up to about 620 nanometers, which is orangish. So it won't get up into visible light, and that'll be really obvious when I show you the spectrograph. But both telescopes can do the basics of taking pictures, blocking out stars so that you can photograph planets around stars, and then taking the light, splitting it by its wavelength so you can see the absorption and emission lines to understand the chemistry of what you're looking at. Then we have the diameter of the primary mirror of the two instruments. Hubble is 2.4 meters, whereas the Webb is 6.5 meters, so quite a bit larger. This is also interesting, the spacecraft mass. The Hubble has all this metal on the outside of it, and it has a whole bunch of additional instruments, and it's got this metal flap, and it was built a long time ago, so it weighs quite a bit more than the Webb. The Webb had to be launched from a rocket, so there's a carrying limit. Plus, even though it has a bunch of other stuff, it's all more higher modern technology, so it weighs less. The mirror in the Hubble is pretty much one solid piece of glass, whereas the Webb has multiple hexagonal segment mirrors that are made out of beryllium, and then they're coated with gold because the intent is to capture light in the infrared range predominantly, and that works better for gold. But you can see here a comparison between the primary mirror of Hubble and the primary mirror of the Webb. And for those that are into, well, how much battery power does it have? The Hubble orbits the Earth, so it's in darkness for a good portion of each of its 90 or so minute orbits. So it needs battery. Whereas the Webb actually has the sun pointing at the bottom of it at all times, and it's got a solar panel on the bottom. So it's never really in darkness, so it has a smaller battery. But the battery technology is newer. This is a nickel hydrate battery, and this one is a lithium-ion battery. So what ranges, what wavelengths can the two see in? The Hubble works from near infrared through visible through UV, and it's got a couple of instruments that work up into the UV range. The Webb works near infrared to middle infrared, and if you just measured out how many nanometers is that, the Webb actually has a wider bandwidth for observing than does the Hubble Space Telescope, because once you get up into the higher frequencies, the very much shorter wavelengths, the total bandwidth is less, because you're not going as deep into the infrared, which are very long wavelengths. So why do we use infrared? We use infrared so we can see things that we can't see in the visual spectrum. For those of you that are familiar with Helen's trip on SOFIA, the Stratospheric Observatory for Infrared Astronomy, a modified 747 with a big infrared telescope in the back of it, you might have seen pictures like this, where if you're looking at a nebula, there's a lot of gas and dust cloud, and you don't realize every one of these little bumps on the edge of the cloud has probably got a star hiding inside of it. But the gas and dust block out the star so you can't see it. But as soon as you start imaging in infrared, you start to see through the gas and dust at the heat sources, all the stars. So that's one of the reasons why you look at infrared, is so you can see more stuff. But there's another reason for looking at infrared. Some of you have heard of the Doppler shift. As space stretches out over time, light shifts more towards the red end of the spectrum. So if you're looking for older and older things towards the Big Bang, you need to look deeper and deeper into the red, and eventually so deep into the red that you need to start looking in the infrared. So that's the idea, is to look deeper into the infrared to see these objects whose light, as it approaches us, has been so deeply redshifted, it's not even visible to the human eye anymore. It's in infrared. This is sort of a banded picture that will tell you what instruments can look at what things. So as you go outward, you say, well, I'm looking in pretty much visible light, and there's your Hubble deep field. And then you can go to the ultra deep field with a little bit of infrared. And then if you want to look even further, they've actually jumped all the way out to the edge. And if they look at the cosmic background radiation in radio, radio is even further, longer wavelengths than is infrared. But we have a gap. We have this area that we haven't seen before from space. And that's where the Webb is going to be looking, is in this deeper infrared region short of radio. So that's the gap that it's going to be focusing on. And just to spread things around and to offer the science up to others, NASA has been assisted by the Canadian Space Agency and the European Space Agency. They have their own business divisions that work with the Webb team at NASA. So it's a collective effort by several international bodies worldwide. People often ask, well, how many people are employed based upon this scientific expedition? And it fans out. So NASA does not directly build these things. It contracts them out to companies, the largest of which for the Webb is Northrop Grumman. But then subcontractors are farmed out by Northrop Grumman to do all the individual little things, to provide more staff to beef it up to get all the tasks done. And so you've got subcontractors like Ball Aerospace, Harris, Coherent, General Dynamics, Global Imaging Technologies, Raytheon, Raytheon Vision Systems, Lockheed Martin, and Teledyne Technologies. And each of these companies have employees that they'll either bring in full-time or contract out. So when you look at the run-up to how many people are behind not just the instrument, building it, testing it, documenting it, promoting it, getting it into a launch vehicle, getting it launched, operating it after the fact. It's a huge fan out. So when you look at the total cost of such a mission, it's not all going to one company. It's really spread over many, many thousands of people being employed worldwide. So where are we launching it from, and how did it get there? Well, this is kind of a convoluted trip. The instruments aboard the Webb are really an international effort, and then they all had to be tested individually, and then they had to be tested collectively as part of the instrument. And the final step in all of that was in Redondo Beach, California, but that's nowhere near the actual launch site, which is in French Guiana in South America. They had to have a ship that took the Webb in a container to safeguard it and to pad it from being jostled about. And that ship actually went from California down the Baja, down the Mexican peninsula, through past a number of Central American nations, and then crossed over the Panama Canal, and then came around over the top of South America down to French Guiana, docked in a port there, and it was hauled overland by truck to the actual launch site. And then current state is it's attached to an adapter, which is attached to the second stage of the Ariane 5 rocket. So that's how it'll actually get launched from Earth, is aboard an Ariane 5 from the Central Spatial Guianas launch complex in Quiro, French Guiana. But you can see the fairings have to split off, and it'll do that fairly early. It just has to get up high enough where there's very little atmospheric turbulence to affect the instrument. So when it gets well above the air pressure, then it'll split open the fairing to allow the instrument to adapt to the vacuum and the temperature of space. But why did they choose an Ariane 5? Well, it had to fit inside the fairing. SpaceX Falcon Heavy sounds good. It could have launched it into where it needed to be, but the problem was it wouldn't fit inside the body of the fairing. So if you look at the Ariane 5, how much larger in diameter it is, even though the Falcon actually bulges out a bit, it needs to be just a bit larger in diameter in order to accommodate it. Now, why is it being launched from South America? Well, when you launch a rocket and you want to give it the most oomph possible, you launch it so that it plays with the rotation of the Earth. And the maximum speed of rotation is closer to the equator. And that's where the launch complex is in South America. It's just 5 degrees off the equator. So there's a bigger spaceship, the SpaceX Starship, that would have provided the fairing diameter to accommodate it and would have had the oomph to get it up there. The problem is it's not well tested yet, whereas the Ariane 5 is as they say, a field-proven successful launch vehicle. Maybe in the future, other things will be launched on Starship once it's proven itself, but at the moment, Ariane 5 was the most appropriate rocket to launch it. And South America was the right place. So once it gets up there, who's going to be operating it? Well, there's a little convoluted food chain of funding to do that. The folks that are actually going to be operating it is the Space Telescope Science Institute. They are also responsible for operating Hubble. So they have experience at doing these kinds of things. And then there is the Universities for Research in Astronomy, AURA. They're operated for NASA by AURA. So there's some AURA governance over the operation of the Webb. Now the Webb itself, this is a picture of the Webb back on Earth before they put it inside the fairing. You can see the size of the mirror based upon the size of the guys working on it in their bunny suits. This is one of the hexagonal mirrors. They're made out of beryllium. And the reason why they're made out of beryllium is glass is heavy. And to make them lighter, they made them out of beryllium. Beryllium is fairly tough stuff, and it does not expand or contract much as it goes from the temperature on Earth to the temperature in the vacuum of space. There's very little distortion from expansion and contraction. So you get lighter weight mirrors. You make them in easier to grind hexagonal components, and you fold the sides back so that it fits inside of the fairing. And you can see that this is one of these sides, there's another side on the other side. They both fold back, and this is the secondary mirror. It's on its own folding assembly. And then the actual ingress for light is through this rectangular opening, and then it hits a bunch of mirrors, and then finally gets to the actual instruments. Here's the folding mirrors on the model. I made them where they fold. That's just electrical tape, but that's what happens is a lot of things have to unfold and be positioned correctly in order for the Webb to begin its mission of scientific observation. So for those of you that might own your own telescopes, how does the Webb compare to your typical amateur telescope? The Webb is a Cassegrain reflector. That just means you've got a mirror, you've got a secondary mirror, and you've got a hole in the back where the light goes out. That's the Cassegrain hole. It's a 3-mirror anastigmat. And what that means is, one, 2, 3 mirrors, and then you have an adjustment so that you can actually point the light coming in to where you want it to be. And if you think about it, if this mirror points light to this mirror, which points light to this mirror, it's off to one side. So that's the mirror that uses to compensate for the tilt of the light coming in. That's the anastigmatic part of it. If your eye has astigmatism because the light's not pointing in the right direction, this is the same sort of thing. You need an additional mirror, a tertiary mirror, to point the light to where you want it to be. The actual focal length of the telescope is 131 meters, very long. The focal ratio is f20. Mathematically, it's actually 19.999, but who's going to qualify as f20? If you think about your amateur telescope, you always like to get the focal ratio to be very, very short, so you can get a lot of light in, very wide field. But the Webb is going to be focusing on very distant objects that are fairly small, so it's not going to be taking in as large a field of view all at once. But there's a counter to that, which is it brings enough light in to actually put light on multiple instruments simultaneously. And I'll show you that later. But being an f20, a particular instrument gathering light is going to need a longer exposure time to get some of those dim objects. And also, the telescope can only point at a specific target, sort of lock onto it and track it for a period of time before, if it stayed pointed that way any longer, then the antennas that are on the bottom of the telescope might not be pointed at Earth anymore. So occasionally you have to reset things so that you can communicate with Earth. So that's kind of the ultimate control over the longest duration exposure. But the way they get around that is doing multiple exposures in a single observing session. So sun's back here, we've got the Earth, we've got the moon orbiting the Earth, we've got the Webb out here at L2, and it's orbiting in its halo orbit of L2. So it can't look behind itself. And if you think about it as, well, the Earth orbits the sun, and if the Webb is always sort of turned 90 degrees to the sun, 180 degrees to the sun, it's not going to be able to look over the whole sky all year long. It's going to have to wait until the Earth gets around to whatever point they need so they can then rotate the telescope around to take a look at things. So at any particular point in time, it can only see about 40% of the observable sky from that position in the Earth orbit around the sun. So if you want to look at a target, if you want to do science, you want to do imaging of it, you have to wait until the Earth comes around, which means you need some fancy software that's going to schedule all that so that to avoid like point here, no, point there. You actually wait until you get around to where you need to point with the least use of fuel. So this is just a little detail about what I was just discussing, which is the orbital distance of the halo orbit varies because it's on an ellipse. It's not only where it is in its orbit around the sun, it's where is it in its orbit around L2. So there's a lot of factors that have to go into it. The thing to point out here is that because of the way it's oriented, it's never going to take a picture of the moon or the Earth or the sun because they're on the bottom side and you want to point to the bottom side. So here's a little bit more of the graphics of the tilting. So you have, as it's referred to as the hot side and the cold side. The hot side's not really all that hot, but it's a lot hotter than the cold side, which is protected by the multiple layers of sun shield. So there are three vectors, V1, V2, and V3, which are the orientations of the telescope. So it can rotate, it can be pushed in and out, and it can be tilted this way. So depending upon what you want to look at and how far it can tilt at any one particular time, it may use multiple of its maneuvering mechanisms for pointing in that direction. So this was a new term that I had learned, field of regard. So if at any particular point you wanted to observe something, how much of the sky could you see? And it's not a flat part of the sky because we have the limits on how much you can maneuver, but it sort of carves out this slice of the sky, which is the field of regard. So if you wanted to look at a particular object, let's say another planet in the solar system further out, like Mars, Jupiter, Saturn, Uranus, or Neptune, you'd have to wait until the Earth was around in that direction and that planet was pointed in that direction, not out away from it, but down from it, so it could rotate around to take an image of it. So there's a lot of factors that go into play into scheduling what it can look at any particular point in time. In addition to not being able to point back at the sun, it can also not point back at the planet Mercury or the planet Venus, because it would be like, yeah, you're pointing back towards the sun to see that. So there are many things it can see, and there are things that it won't be able to see. So it's good that we still have other instruments out there like Hubble that can see those things. Which instruments can see what in what wavelengths? So there's a number of instruments, and here's the wavelengths of the particular bands that it can see through. So we have near infrared, and notice that there's NIR CAM, NIR SPEC, NIR ISS, and then the fine grain. But what you have here are all of the near infrared related instruments. So they can see in this range here. Now, in the astronomy, they were used to using nanometers because we also do radio. But as you get to very large nanometer values, like 1,000 nanometers, you start to move up into microns, which makes the numbers smaller once again. It's just factoring that metric stuff. So that's why this scale up here looks to be a much smaller set of numbers than our usual nanometers measurements. But there's another instrument aboard called MIRI, and MIRI can see more into the mid-infrared. Now, most of these instruments have spectroscopic capability associated with them. So not only can they see in that band, they can also do spectroscopy or to produce spectrographic images. Now, if you were to take a look at the backside of the mirror, you'll find where the instruments are. Remember, the light comes in from this side, bounces off the primary mirror to the secondary mirror, goes through that object at the front, the entrance right here, and then it goes to the back of that, bounces off the tertiary mirror, and then hits the instruments. The instruments, when they operate, they produce heat. They need to vent that heat. So we have this aft deployable infrared radiator system. It's just multiple panels of aluminum that is high purity aluminum, and it dissipates the heat off the instruments, has heat pipes running through it. Okay, so most people are familiar with digital cameras, and they take color pictures. Since the Webb is intent on infrared, through red into a little bit of orange, not into visible color, you're not going to see images that include yellow, green, blue, or violet unless they've been artificially colored. And if you're used to doing the narrowband imaging or hydrogen alpha, you're already familiar with the colors that you're seeing in the image aren't visible to the human eye, so they artificially color them. So if you ever see an image from JWST and it has yellow, green, blue, or violet, those colors will be artificially enhanced to show out some particular observation that they're trying to make stand out. The near-infrared camera operates from 600 to 5,000 nanometers, and MIRI is more in the mid-infrared. It goes from 5,000 to 28,000 nanometers. So the instruments can operate as imagers, so it can take pictures. It can operate as a coronagraph, so it can block out the light from a star to take pictures of things around the star. And it has two kinds of spectrographic capabilities. One is called slitted and one is called slitless. And all that means is, will the light go through a narrow slit to kind of block out as much as possible except for a little slit of light? Or does it take an image and then pulls the various wavelengths out of the image to get the spectroscopic capability? And which instruments it's using and for what wavelength of observation all have to be taken into account by the observation scheduling software to not only know where you need to look in the sky, but which instrument and how to operate it. So for those that might have seen digital cameras in association with amateur astronomy, it's usually a chip that has sensors on it, and it captures photons, converts them to electrons. You read out the electrons, and lo and behold, you have an image. Well, if you're going to send an instrument out to L2, you want the biggest possible bang for the buck, and you don't want to have to have every image be the longest duration possible. You might want to have the ability to adjust the image size and duration so it actually has multiple imagers in each instrument. So you can see the multiple image capabilities that the MiriCam has and the different sizes of them. Now it says cooled by liquid helium. It's not actually cooled by liquid helium. It's cooled by an instrument that takes the cold of space and then through recycling of a thermal conductor will actually drop the temperature lower and lower and lower. Cooling with liquid helium is something that is sort of a leftover from an early copy of the presentation that I did. I just didn't get that one. Spitzer was cooled by liquid helium, and we'll get into the pluses and minuses of that. But much as our amateur imagers have the ability to get different wavelengths of light into the chip, there are filter wheels that can also be put in front of the chip to adjust what wavelength it's going to be focusing on. And here's the NearCam. The NearCam is even more complex because it actually has filters that can take two images in different wavelengths at the same time. So that'll be interesting to see what kinds of things it can take images of at the same time. Short wavelength and long wavelength have different sizes of imaging. It has to deal with not only the gap between the imaging chips, as well, you can't take a picture there unless you're using the big array, but also there's a gap between the two chips. Module A and Module B are two different groupings, and if you want to take a picture of something that's incredibly huge, you'll have a gap in the middle. If you want to take a picture of one of these galaxies, then you need to make sure it's not lying on top of the gap. So that's another part of the scheduling, is to make sure that whatever you want to take a picture of, you understand the size of it and make sure it's not falling into the gap like this object is here, because then you're not going to get any signal from it unless you use the whole imager. Spectroscopes. So most of the instruments can be used in a spectroscopic mode. And if you were to just look at the range of wavelengths available, a lot of it looks red and orange. Funny that, because you're looking in infrared and getting into a little bit of orange, but that's it. So you're not going to see any yellows, greens, blues, or violets. So what you're going to look at is the absorption and the emission lines. So the bright ones are the emissions and the dark ones are the absorptions. The absorptions will tell you the chemistry of the source of the light. So you can tell, has it got any copper in it, or has it got any hydrogen in it? Numbers of different elements it can pull out based upon where the lines are. And this is my favorite instrument, the NearSpec. It has 250,000 individual little shutters. But this is not a pencil point. This is actually a probe that's pushing on one of the shutters. And what it can do is it can block out light. If you looked at the Kuiper mission, the Kuiper instrument could see a larger area of sky. I say larger, it's about as big as your little finger. But when it was looking in an area, if there was a bright object nearby, it basically bloomed out and you couldn't see anything near it. And what these shutters will do is block out the light from areas you don't want to take pictures of, so that you can take pictures of the dimmer object next to a brighter object. So it'll be interesting to see how all of this pans out for the Webb, as to, if you set the shutters just right, you can actually do observations of different targets in a single snap of the camera. Okay, so what things can it detect in the spectra that it can view? So we already mentioned the range in nanometers of the various instruments. Well, in those ranges, what kinds of molecules can it detect? What kind of absorption lines will it have? There's methane, so we can detect methane in the atmospheres of exoplanets. Water, nitrous oxide, carbon dioxide, and ozone. There is one line of water that's not detectable because it's in the gap between the two instruments, but we can indirectly detect it by looking for things like ozone. So where there's ozone, which is O3, there's also likely to be O2, which is diatomic oxygen. So these are the chemistries we're looking for with the instruments that we have. But some of these are indicators of what's going on a planet. Now, exposure times. You're used to in astrophotography just going, I want to take a picture of that. You open the shutter or whatever to the imaging chip. You gather a sufficient amount of light, varies based upon how dim it is, and then you close the exposure, and then you drain out the electrons that you built up. You get a voltage, and there's your picture. Can't quite do that with the Webb. What you have is a multiple step process. It does what is known as non-destructive up the ramp sampling, which basically says if you want a long duration exposure, you bracket that into multiple shorter duration exposures and you check the individual exposures. I'm sure that amateur astro imagers have sometimes gotten a bunch of images and then they see that one of the images, one of the frames that they took in their stack had a light in it from a local flashlight or a satellite going by or a car driving past where you're observing, and you have to discard that frame. Well, the Webb can actually do that as it's gathering the light. It can go, wait a minute, that's a bad sample, and discard the sample or put it into a discard bin and then gather up the rest of the images. So you have the number of integrations in an exposure, you have the number of groups in an integration, and the number of frames in a group. And it can examine the individual frames as it goes along to go, oh, did we get a cosmic ray hit? I know that for some of the images that you've seen of sun observing instruments, when it gets a blast of radiation from the sun, you see the image all gets distorted. And then as it dies down, you can start imaging again. Same sort of thing, but it'll be able to do this as it's processing the images. The total exposure timing will be roughly the same as Spitzer and the Hubble's wide field imaging camera. But the maximum duration of exposure has other things that might limit it. The Webb is in this halo orbit around L2. So as it points at something, if it gets to the end of the orbit and it has to come back around the other direction, it's going to have to change its position relative to the radiation coming from the sun in order to orient itself. When it does that, it might not be a good time to observe that particular object. So that's another scheduling thing we have to think about is how long an exposure are you taking, pointing at what direction before you're going to have to move the telescope. Earth communication takes place 1 to 2 times per day because you can only store so much in the flash RAM that the instrument has. So about every 2.7 hours, it's going to have to sort of adjust itself to make sure that it can stay in contact with the Earth. Now, as I said, there's multiple instruments, and the light coming in from the front of the telescope can bathe all of these instruments. So depending upon what you want to look at with which instrument, we'll say what things are having light shine on the focal plane. So this large area that's here is the focal plane, and you can see how the instruments are spread around it. The instruments don't move around within there; they're fixed on the focal plane. But what they can do with a tertiary mirror is to adjust where it's pointing light as to what part of the sky is going to show up in which instrument. As I was saying, the telescope itself is in an orbit, so it's rotating to compensate for pointing at the same object for an extended period of time. And that's these 3 vectors, V1, V2, and V3. Well, it can do that for a certain amount of time, finely aligned. And the way it does that is the same sort of way that we do it with our telescope cameras. We have a guiding camera. Well, the Webb has 2 star tracking cameras, and it will keep itself lined up on that. But it can also make use of its momentum wheels, kind of like gyroscopes, to keep itself oriented. But it'll get to a point where it's going to have to stop and then move and then resume its imaging. If in its new position, it can still see the same target. So the sun shield, it counts heavily upon this to keep the hot side down and the cool side up. So there's 5 layers of this reflective foil material is used to keep the heat away from the instruments. It's also used to keep the exhaust nozzles of the orbital maneuvering rockets so that the debris that comes out of them doesn't find its way back onto the mirror on the front side. And the communications antennas with Earth are also on the bottom side. And you can see the 2 star trackers there on the bottom. Now, propulsion. It has, the Webb has multiple propulsion systems. It uses one set of thrusters to get it to L2. And then once it's at L2, it uses 8 thrusters to orient itself. Remember, it has pitch, roll, and yaw, these B1, B2, B3, and it has multiple thrusters in different directions. So it can orient itself however it needs to point itself. But they all consume fuel, and it's not getting any more fuel. So once it launches, that's as much of this long-term fuel as it's going to have. And that ultimately becomes the limiting factor on how long the Webb is going to last, is when it runs out of this fixed supply of fuel for positioning itself, it's not going to be able to keep on targets as well anymore. It can still use its momentum wheel. It can still use the solar momentum flat panel to use the push of the sunlight, much as the Kepler mission used the sun solar wind pressure against it to compensate for the loss of a gyroscope. That's the limiting factor. MIRI instrument, which is cryogenically cooled, does not use helium for that. So it's not like Spitzer, which ran out of helium and had a warm period. The Webb will be cold until it runs out of maneuvering fuel. You've probably heard of solar wind and solar sails. Well, that flat panel on the front of the Webb is a segmented solar sail. It's not using it to move large distances. That's what the thrusters are for. It's using it so that it can hold its position using the solar wind as a source of pressure to allow it to stay on target. It also has 8 momentum reaction wheels so it can orient itself. But the reaction wheels, once you spin them up, they have a top speed. And once you get to the top speed, they will not help you on orienting things any longer. You have to actually spin them back down, use your thrusters to reorient yourself, and then you can use the reaction wheels again. So they have an ultimate maximum compensating force they can supply. And outside of that, they're going to need to keep the Webb in its halo orbit, and they do station keeping firing of the thruster rockets about every 1 to 2 times a week. Okay, so attitude control. How does it keep it pointing at targets with a fine enough tracking so that it can do long duration exposures? It uses the reaction wheels to get it to the basic position, and then it uses the same thing we use. It uses a guiding camera, these 2 star trackers, lower resolution. They're only 512 by 512, and they're CMOS cameras, just like we would use on Earth. But what they'll do is they'll track a star in the field of view. You've got 2 star trackers, you can have 2 coordinates. So once it's at a target, it will then use the fine guidance sensors to track on a single star. And it will be able to stay on target with that for a certain period of time. That's very similar to the guide cameras on amateur telescopes. You probably have heard of the ST4 interface or the application known as PHP guiding to guide it. Well, fancier software, more sophisticated interface, but it's still providing fine guidance by tracking stars. So how does it talk to Earth? Remember, the antenna's on the bottom side, and it uses a modified Raytheon Eclipse Common Command and Telemetry System. There's a NASA acronym for that, CCTS. And it actually has 2 sets of frequency ranges that it runs the radios on. And it has an 8-inch S-band. That's for command and control kinds of things, and for low speed data just to say, how are things going? Where are you currently pointing? Is everything going okay? And then you have a broad beam that's a different frequency range to give it up to 40 kilobits. But then it has another set of radio in the Ka band, which is in the 25 to 27 gigahertz range. That's a stronger transmitter, and that's for the higher speed stuff like transferring images, wide spectrograph images, and that can get at 7 megabits, 14 megabits, or 28 megabits, depending upon conditions. And the conditions could be noise in space, or if the instrument is at the edge of its orbit and it may not have full gain on the signal from Earth. Now on Earth, we have this thing called the Deep Space Network, and I've discussed that before in a previous session, where in order to have, as the Earth rotates, constant contact with things in space, you have these 3 arrays of radio dishes that are transmitters and receivers, and they're spaced 120 degrees apart on the Earth, so that as the Earth rotates, if you want to stay in contact with something, you can. It will use the Deep Space Network to do that. Now, if the particular station that it's using on the Deep Space Network is, let's say, in California, then it will probably use a ground level transmission to get to the Goddard Space Flight Center, where the folks operating the telescope can work with it. But if the if the radio telescope array is, let's say, in Spain or in Australia, in order to get the highest speed data transfer, it may actually go up to an Earth orbiting satellite, which is the NASA Space Network, not the Deep Space Network, but the Space Network. So the signal will go from the Webb to the Deep Space Network on the Earth, maybe back up to a satellite in Earth orbit, back down to another station, and then over a landline, over a fiber optic high-speed landline to the Goddard Space Flight Center. And it's switching this on the fly. So there's a team effort to make sure that when you want to talk to it or get data from it, that you can. For those of you that might have been following the Deep Space Network, they had to have a couple of stations out of commission for a while they made upgrades. The upgrades to the Deep Space Networks were so that the Webb could use the existing X-band radio communication because it's so near Earth. You might not think of 1.5 million kilometers as being all that near, but considering that the Deep Space Network is talking to things out beyond Pluto, out at the edge of the solar system, like Voyager 1 and Voyager 2 and New Horizons, it's not used to getting a signal that close to Earth. So they had to adjust it so that they could use the Ka band for such a near target for high-speed download. So because it's so close to the Earth, relatively speaking, this will be the first high bandwidth spacecraft that will communicate with the Deep Space Network such that if it loses a packet of data at high speed, it will actually be able to get it retransmitted, because the distance is so short that, what's a few milliseconds? Actually, what's a couple of seconds? If you think of, if you wanted to get a retransmission to something from New Horizons, it would take many, many hours, and it's much better to just receive it, and if you don't get it, drop that on the floor and keep receiving. But in this particular case, it will actually be able to tell the Webb scope, I didn't get that last frame, could you send it again? And it may come later, but it will be a few seconds downstream, and it'll retransmit it. This is the first time that they've been able to do that. So that'll be an interesting thing. Now, storing and downloading the data. As the Earth is rotating, even though we have the Deep Space Network, the receiving stations on Earth and the telescope may not be in sufficient alignment, and it may have to move the telescope. Well, if it adjusts the telescope, you can't be doing imaging any longer. So to make it where it can image for a longer period of time, the Webb has a 65 gigabyte solid state data recorder. It's got a big flash drive on board, and the amount of data it can hold is relative to the amount of data that the instruments can collect over a period of time. So while it's doing data downloads, it has to be best pointed towards the Earth for the highest possible data transfer rate. So when it's doing that, it can't be imaging, can't be doing its science. So there'll be 2 4-hour contact periods per day, approximately 12 hours apart. And it will be talking with Earth. Well, that means it's got to gather data, store the data, point towards the Earth, transfer the data as fast as possible, and then going back to doing science. Well, that means that you're going to store a certain amount of data, and then you got to transmit it. If you can't get it transmitted out, you may be limited as to what science you can do because you're already storing valuable data and you don't want to overwrite it. So you may have to wait until another opportune period to send the data down. The Webb is closer than other targets that the Deep Space Network looks at. And the Deep Space Network has to talk to all these other things. And some of them are operating on very similar frequencies that are deeper into space. So the coordination of what I'm going to image, do I point at it, what instruments, what kinds of filters, how do I adjust the instrument's exposure? Plus, if I gather that data, how soon can I send it back to Earth? And will the Deep Space Network be talking to me at that point in time? Or will it be sort of frying better fish talking to Voyager or something? So all of those things have to be taken into account for the scheduling of the scientific data gathering, and then the scheduling of, now that you have the data, getting it back down to Earth. So it's not just point and shoot. So what are the objectives of the James Webb Space Telescope? In order to get your observation, you have to go through and submit a proposal, and the proposal has to be analyzed as to, can we see that? When can we see that? What instruments do you want to use to see that? Are you using it in imaging mode or spectroscopy mode? Do you need to obscure a star, coronagraph kinds of things? So all of that has to be taken into account. And there are multiple cycles of processing of proposals. So the possible targets of the Webb are brown dwarf stars, galaxy clusters, the debris disks of planetary systems, deep fields, some wide, but deep field images. How many galaxies can we see in how small an area of space when we expose for the maximum duration? If we use it in coronagraph mode, can we see exoplanets? High redshift targets. Now, these would be things that are many billions of light years away and so deeply redshifted that they're actually in infrared. Protostellar regions, protostars. Now, you can't image the black hole itself, but can we image the illuminated disk around a black hole? Star-forming regions, because we can see through the nebula gases and dust. And then taking a look at certain galaxies that we want to gather detail in infrared. Plus, if they're in the right part of the sky with the right instruments, it can actually image solar system objects like Kuiper belt objects, trans-Neptunian objects, near-Earth objects, Jupiter's red spot, Trojan asteroids. We've got something going out to look at those. The moons of planets in our solar system that we might not be able to image from Earth, but given where the Webb is, we might be able to confirm some of the moons that, for example, have been seen around Jupiter and Saturn, but haven't been confirmed by a second spacecraft going by. So it may be able to confirm some moons. And then there's specialty categories of things that you can do with the Webb. There's general observer programs. This is the GO, and there's how many hours it can allot to this over the what period of time, and it starts 6 months after it's operational. But the director's discretionary early release science, this is the good pictures early on. That starts 6 months after it's operational and has a duration of about 5 months. So once it's operational, you can expect there to be nice looking images during the first 5 months. Then there's guaranteed time observations. These are for critical observations for science research programs, and they'll get 16% of the first 3 cycles. But the first thing you have to do is calibrate the instruments, and from time to time, it may need to confirm the calibration of its instruments. Which instruments to calibrate first? Well, the first thing you're going to have to do is calibrate those hexagonal mirrors that make up the primary mirror. So those have to be oriented so that all the light converges onto the secondary to get all the light to converge onto the field of view. Then the fine guidance sensor, those 2 star trackers, those have to be calibrated as well. Absolute flux calibration. How much light are we getting in from which instruments so that we don't bloom them, so that we don't overexpose them. And then the instruments themselves have to be calibrated. And then once the current set of approved proposals has been approved, and most of them have at this point in time, because they do this well in advance, then there's further planning for follow-on observing sessions, more proposals to come. And it has to go through planning them out, confirming them, getting the budget money allocated to do them. You don't get your web time for cheap. And then once you've done it, the data has to be stored and analyzed. And it's typical that there's about a 1-year lag between recent observations and then defining that as good calibrated scientific research data, and then people producing papers or reports based upon that data. Now, how long is Webb going to be up there? Well, if you think about the Hubble, it was expected to have a mirror lifespan of 15 years. It was serviced a couple of times by the shuttle, but it's been up there 31 plus years. Unfortunately, we can't expect that same duration from the Webb. I'm sure they'll try, but at some point when it runs out of its supply of attitude adjustment fuel, it's not going to be able to keep on target as easily. The reaction wheels will still work unless bearing problems happen, which happened with the Kepler. So they will keep it operating as long as possible, but the fuel supply is estimated to have a 10-year lifespan, and that's all based upon not using up too much of the fuel for specific observing sessions, because depending upon what you want to observe, it may require more fuel than another observing session. So they will have to optimize fuel consumption. Then there's other things that affect its longevity, which is solar panels. And if you've seen what they've done with the International Space Station, they've replaced a number of the solar panels and added more solar panels over time as the technology improves, but also as micrometeoroids and solar wind abrade the solar panels, and they don't produce as much electricity. And then even lithium-ion batteries over time, if you manage the charging and discharging of them, they're still not going to hold their charge forever. The good news is the MIRI instrument, which has a cryocooler, it recirculates pressurized gas. So think of it like a very low temperature freezer. So it should remain cold through its course correction fuel limit. It won't have a helium fuel limit like Spitzer did. Spitzer went into a 2.5 years of cold life and 5.5 years of warm life because it exhausted its helium supply, and JWST won't have that because it uses a different approach for cooling the instruments. Now, given that it's at L2, the Webb is not expecting any servicing missions like we did with Hubble using the shuttle. However, just to be on the safe side, the Webb does include a capture bracket. So if sometime in the next 8 to 10 years, we actually do produce spacecraft that can get out to L2 and possibly service it, there's a capture bracket just in case. Now, what is it specifically expected to accomplish? NASA's never going to send something up there and go, well, we'll wing it, we'll ad hoc it. No. Its goal is to see deeper into the universe than other instruments because it's looking at from a darker place in the sky, a colder place in the sky. It's going to have more sensitive instruments. It has a larger primary mirror. And because it's deeper into infrared, it can see things that are more red shifted towards infrared. So it can see back earlier into the formation of the universe. And it'll be able to, because it's looking in infrared, see the faint disks of planetary formation around distant stars forming solar systems. And if we're real lucky, now that we've confirmed that there's planets that are even bigger than the biggest Jovian planets that we've thought of. There was an expectation that if you get a planet larger than about 4 times Jupiter's size, well, it's really a brown dwarf star. Well, it turns out, no, you can get things that are planets that aren't stars even bigger than that. And if you get one that size and it's orbiting some distance from its parent star, the Webb might actually be able to image sort of a half moon kind of image of that. So as it orbits its star and it gets out from its star, the light will shine on one side of it. And from our perspective, we're looking at it this way, so we might be able to get an image of that planet. But if we can at least see the atmosphere of that planet, we can do a composition analysis using spectroscopic imaging to tell what is the chemistry of the atmosphere of that exoplanet. Well, the Webb is expected to last 10 years, maybe a little longer if we do some optimizations, but you have to eventually plan for what comes next. The decadal survey released in November of 2021 by the U.S. National Academy of Sciences, Engineering, and Medicine identified what space-borne instruments should get funding in the future. And one of them is one that's already in process, which is the Nancy Grace Roman Space Telescope. It was formerly known as WFIRST. It's also infrared. It's scheduled to be launched in the mid-2020s. Once Hubble's at end of life, we're going to need something that can see in other than infrared. And since the Webb only sees in infrared, and we're considering more than 10 years down the road, we're like 20 years down the road. They're already planning for even larger telescopes, assuming we have launch vehicles that can piecemeal assemble them out in space. And the Large Ultraviolet Optical Infrared Surveyor, or LUVOIR, has 2 different models of that, an A and a B, that are planned for the late 2030s. So we're looking well ahead. And it did receive some funding to sort of kick things off and get things rolling. Because if you remember with the Webb, it took a long time from, I think we ought to build one, to actually having it launched. But we need to gather more photons. And here's the scales. So if you see on the left, we have the primary mirror of the Webb. And you can see it's a Cassegrain because it's got a hole in it. The HAB-X, a little bit bigger. And then the Webb, 6.5 meters, it's Cassegrain. LUVOIR B doesn't have a hole in it, which says it's probably going to have a camera out where the secondary is. So it's not going to be a Schmidt-Cassegrain, it's going to be a Schmidt camera. And then you have the gigantic 15-meter LUVOIR A, also a Cassegrain. This one's going to have to be sliced up into multiple sections. And if you look at the colors of the mirrors, this one works in optical through infrared and ultraviolet a little bit on each end. Same here. The Webb is more focused on infrared and deeper into infrared, so it can use gold mirrors. LUVOIR B and LUVOIR A, they're going to be more in the visible range, so they're not going to be able to see as deep in infrared, so you don't have the gold reflective coloring, but they're going to be able to see more in visual and a little more into ultraviolet. So that's what's planned ahead. Where they're going to be and when they're going to be launched and what kind of instruments they're going to have on board. They're planning all that stuff out now, and we'll see as the years go by. So for those people that are into making printed paper models of NASA instruments, we have, let me turn it so that the beauty side is there. We have there is a web model. So for people that like to build paper objects, it's hollow on the inside and sort of flimsy, but it's good for going, look, there's the primary, there's the secondary, here's the radio antennas. So it's good for showing off the basics. There's the solar panel. But that's an easy to build item. NASA does have a 3D printable model. It's a solid model, but it's designed to be printed on resin style printers or STL style 3D printers. And since I had a filament style 3D printer and NASA didn't provide a 3D printable model for my kind of 3D printer, I took it into my own hands, and that's where this one came from. So this is more than 50 pieces it took to build this. You can see in the picture on the left. This is before I assembled it, all the individual little pieces. And then I assembled it, and you can see the top view and the bottom view. And if anybody's truly interested, I can provide the CAD files to do it. It takes a couple of days to print all the pieces. And I actually bought different colors of filament so that I would be able to show off and make distinctive different parts of it. It's easier for me to print using different colored filaments than it would for me to paint them. And if you've ever seen the artist rendering of the James Webb Space Telescope, I tried to get filament colors to match pretty much the artist rendering. So I've been your presenter, and Will has been our subject matter expert. I haven't had to count upon him at this point, but I would like Will to just unmute and tell us anything that we missed or got wrong, or anything additional you want to add.
Well, I could say a little bit about the kind of science that I'm hoping to do with Webb.
Excellent.
I'm on a couple of teams that have those GEO General Observer Cycle 1 proposals accepted that Monroe was talking about. And there are sort of four main science teams for Webb. And of those, the one that I'm sort of most involved with is protoplanetary disks and the origin of solar systems. So for quite a few years, I've been working on problems related to how stars form. As you know, we've discovered thousands of planets orbiting other stars, and to understand like how those planets form, we have to know how their stars formed. So we've done lots of work with the Spitzer Space Telescope and the Herschel Space Observatory to find where the protoplanetary disks are within the nearest 500 parsecs or so. And with Webb, we're going to make detailed follow-up observations of a few of those. Because, you know, those previous missions were smaller telescopes and could map large parts of the sky. Webb isn't really a good mapping telescope, but it's got the power and resolution to do really detailed studies of just, you know, things that you already expect to be interesting. And what we're trying to do is, so let's see. So we were looking at a few spectra of stars that showed like those absorption bands. Normal stars have absorption lines in them, but very young stars have emission lines. And the strengths of those emission lines tell you how rapidly that star is gaining mass from its disk. If we look at stars that are a few million years old that we can see from the ground with near-infrared telescopes, those emission lines tell us that the stars are basically all formed. They're accreting maybe 1 moon's worth of mass onto the star per year, which isn't that much. We're hoping with Webb to discover stars that are accreting something more like 10,000 moons worth of mass onto the star per year. We're trying to find when during the star formation period is the star itself really being built up from that disk. It must be before a few million years, so it's maybe tens to hundreds of thousands of years. And because Webb is optimized for the infrared, we can pierce through all that dust that these protostars are embedded in and learn something about, you know, how the very youngest ones are forming. And maybe a year from now, or well, not a year from now. Yeah, maybe about a year from now, we're hoping to get our first data on some of these stars. They happen to be in the Orion star forming region.
So out of curiosity, I do have a question for you, which is, so your bio shows that you have some experience with SOFIA. Our folks are fairly familiar with SOFIA. Helen's done a number of presentations on it. So what was your interactions with SOFIA?
Well, I think twice now I've actually flown on SOFIA while they take data. They offer you the opportunity to do that. Mm-hmm. And what I do with SOFIA is, one of the things that happens when stars form is they can occasionally, they're always undergoing sort of low level variability of about a magnitude scale or less from day to day, week to week. But occasionally these young stars will have these major outbursts where they get 100 times brighter over the span of just a few months. And with SOFIA, we can monitor those outbursts and see how the luminosity changes. And that tells us something about how mass is accreting onto the star. So we've been using SOFIA to study these outbursting stars at mid-infrared and far infrared wavelengths. It's really valuable because that's all we have. Webb is going to go out to mid-infrared, and SOFIA has far infrared capabilities, and that's the only way we're going to be able to observe the far infrared universe anytime in the foreseeable future.
Okay, thank you. So does my audience have any questions?
Yeah, I have a couple of questions. So when we're talking about it observing the infrared spectra, are we talking about looking at things that are emitting the infrared spectra now, or we're looking at things that are back in time that were emitting ultraviolet and visible light, and now as space has been stretched, that it's infrared now, but it wasn't infrared before?
I would say both, really. It sort of depends on the science you're doing. Like the sort of things I'm interested in with protoplanetary disks, those are pretty nearby. And there we're looking at the dust emission in mid-infrared wavelengths. The cosmologists and the galactic astronomers, in many cases, are looking at very distant objects that emitted in what we would call the rest frame, ultraviolet and optical light that's being redshifted to those long wavelengths.
And when we look at the light that was emitted a long time ago, so let's say we're looking at something that has a characteristic blue spectrum like copper or a green spectrum, and we can't really see those. Are we still able to do a chemical analysis of the sort of deep time emissions that have been stretched just by calculating the shift in spectrum?
Yeah, the relative positions of all those different emission lines are still the same, just shifted to longer wavelengths. So, instead of a hydrogen line at 6,000 angstroms, it'll be out somewhere at a few microns. So you can do kind of the same analysis you would after correcting for the redshift.
Thank you.
So do we have any other questions?
Yeah, how far back are we going to be actually able to look all the way back to the creation of the first stars right after the Big Bang? The first generation?
Yeah, I think it's accurate to say that. Like I'm not sure quantitatively, like exactly how far back we can look, but Hubble already is seeing kind of the beginnings of galaxy formation. So I think Webb should be able to go back to the very beginning of that.
If you go back any further, you're looking in radio.
Yeah.
And then all you get is the cosmic background radiation, and you don't see any formations in that early, bright and dark.
Hello. This
Hi,
is
Joanne.
Joanne. Hi, I have a question. It's
Sure.
off topic, though. Am I allowed to ask an off-topic one about his history of how he got into space and, interested in that kind of thing?
Well,
Yeah,
it's up to him. Yeah, I guess you can ask him.
yeah, I can talk
Okay.
about that. I think for me, it really started when I was, before I started school, even, we had a library within walking distance from our house. I was born in Canton, Ohio, and my mom and I would put my baby brother in the wagon and we go to the library. And this was right when the first books were getting published with images from Voyager 1 and 2. So, as a kid, I saw like these close-up high-resolution images of Jupiter, Saturn, Uranus, and Neptune. Maybe not Neptune quite yet. It's a little earlier than that. But that kind of got me interested in space. And I went to the University of Toledo for my undergrad studies in Ohio, and they had a strong physics program, but also a 1-meter telescope right on campus that you could do hands-on work with. And that turned out to be pretty good preparation for kind of my career sort of has a technical focus, and that was kind of a good way to get started on that. Stellar spectroscopy was kind of the focus of what we did with that 1-meter telescope, and I still do a lot of work in that sort of thing.
Thank you. Very good.
Okay, any other comments or questions? All right, then. Thank you, Dr. Fischer. This was wonderful. And if there are any opportunities for doing these sorts of events in the future, I'm sure I'm on the email list of Goddard or some other organizations to see if see if our group is interested in it again. But thank you very much for your efforts both before and during this event. And I guess we can let you go at this point.
All right. Yeah, you have my contact information, so feel free to stay in touch if you have more questions. And we're all eagerly awaiting the launch in about 10 days and a few hours.
Okay. Thank you very much.
Yeah, thank you.